Right, so welcome to this video where we're just going to have a walkthrough of some of the key questions that have come out from reviewing your work. I think it's fair to say it's a bit of a tricky exercise in places, this one. So, as I say, having had a look through the work that you've been doing, generally all stuff looking good, looking at the right sorts of things, but some of the questions a bit trickier. Question 3 and 8 really seem to be misplaced in the exercise, being as early as they are. Question 16 is definitely easier than 3 and 8, and so are most of the other questions in the exercise. So we'll dive in and we'll have a look at some of these ones anyway. I know I've been through a couple of these with some of you already, but just in case you've missed them, and we'll come through. And obviously, if there are any others you want me to look through at any time, just give me a shout, and it's no problem. We can get on a call and we can have a look at these. So here's the question 3, which I have been through with some of you. And just the first thing to think about on here is it looks tricky, and it is tricky. Okay, it's a difficult question because it's not really telling us all that much to start with. We know that distance from the satellite to the moon in the question is given as 16,000 kilometers, so we can fill that in there. We know we've got this parabola that goes through the origin, and its axis is along the x-axis, so that we know that absolutely it just has this form, y squared equals 4ax. We can be sure it's like that. There's no offsetting in the y direction. There's no offsetting we need to do in the x direction in that. It's just y squared is 4ax. So once we've got a, we've got the parabola. Okay, that's all we need to do. Once we've got a, we've got the parabola. So we just need to think about how we do that. Now, ordinarily, if we'd got a point, let's call this point S, where the satellite is. If we've got a point that was on the curve, we'd just substitute in the x and y coordinates, and we'd use that to work out what A is. That's what we've been doing a lot. Okay, one of the really key skills on this internal is being able to take a point that you know is on the curve, substitute in, and use that to work out any constants. But we know the distance here and the angle. We don't know the x and y coordinates straight off of that satellite. Okay, but we know its x and y coordinates do satisfy that equation. But can we determine what the x and y coordinates are from our diagram? Can the diagram do some work for us? Well, there's a 30 degree here. There's a 16,000 there. So I've got a hypotenuse really, if I think about it, and I drop down this vertical, this perpendicular there to the axis. Now the distance here across this dotted line is in fact the y coordinate of S, isn't it? It's the y coordinate of S because there's my y level, that's where y is, if that's the y coordinate of S, and I've gone all the way down to 0. So that distance there is the y coordinate of S. But y then, here is the opposite, and there's the hypotenuse, and there's the angle. So simple trigonometry tells me that y is the hypotenuse times by the sine of the angle. Okay, the sine of the angle, sine of 30 in this case, because we're dealing with the opposite, and we already have the hypotenuse. Now, sine of 30 is actually quite easy. It is a half, so I will just end up with 8,000, and I know my y coordinate, so that's good. Seems like I'm onto something that's going to help me with this equation. Can I do something similar to get the x coordinate? Well, wouldn't it be really nice if the x coordinate was equal to this distance here? Because if it was, I can use that same triangle, but instead of using sine, I can use cosine. But that's not right, is it? Because this is x here, which means this distance here is x. All right, this smaller distance from the y-axis across to the x position of our satellite. But I can work out what this is, and I do know, this is where we're really bringing in the sort of high-powered thinking around this, I do know what all of that distance is, or at least I've got an expression for it, because that's the distance from the vertex to the focus where the moon is. And we know if we've got an equation y squared is 4ax, that focal distance is a. The focal distance is a, distance from the vertex to the focus. So if I can work out what this length is, let's just call him L for now, I can take that away from a, and that'll tell me what x is. You might be thinking, well, how's that going to help me work out a? I don't know a, that's the whole point. If I knew a, then I'd done the question. Okay, I've worked out the equation of my parabola. But what we're going to do, if we get our expression, and our expression in a moment is going to tell us that x is the focal length minus the length in that triangle from the cosine. Now, I can say the length in the triangle in a similar sort of way is 16,000 cos 30. So I've got rid of a variable there. I'm just going to bring a number in. Cos of 30 is root 3 over 2. All right, you can leave it as a decimal if you want, but I'm just going to leave it as root 3 over 2 because that comes out quite nicely for me. Root 3 over 2. So actually I'm talking when I should be paying attention to what I'm doing when I'm writing. So let's get that back right. So root 3 over 2 times 16,000 is just going to be 8,000 root 3. Yeah, the root 3 over 2, the over 2, the divide by 2, and the 16,000 bring me down to 8,000. So I've got an expression for x, a minus 8,000 root 3. And if I bring that into my equation up here, y squared equals 4ax, I can say that y is 8,000. I can say I've got 4 times a times all of this. Now, do you see? That's just going to give me an equation just with a's in it. And because it gives me an equation just with a's in it, I can work out a. All right, or at least I hope I'm going to be able to do that. So let's write it's 4a times x, but x is just a minus the 8,000 root 3. All right, at this stage, once I've done a bit of tidying up, at this stage even, I've got an equation that's just in a's. Just got a in it, so if I can manipulate it somehow, I should be able to solve it. Notice I'm going to get an a in front of the bracket times by an a inside the bracket, and a squared will come out. That's going to mean that I'm going to have a quadratic equation. A squared will occur, so I'll get a quadratic equation. Let's have a look. 8,000 squared, well, I'll get 6 zeros on the end with them, won't I? Because of the 3 there, and squaring it will give me another 3. And I need to square the 8. So I'm going to get 64 million. Quite a big number. 6 zeros because we had the 3 zeros above. 4a times a, multiplying out the bracket. Well, that's the 4a squared. And then I've got 4a times minus 8,000 root 3. Well, 4 times minus 8,000 will give me minus 32,000. And I've got root 3 and an a still around. Always write the letter at the end, yeah? In algebra. So we're left with a quadratic equation, really. Okay. If I like, I just take everything over onto my right-hand side. I might want to divide by 4 as well, because 4 goes into all of this. It doesn't really matter so much at this stage. I mean, if I was going to try and factorize it, that might be a good thing to do. But I'm not going to try and factorize this one because it is something that looks like it's not going to be too amenable to factorizing. So I could either use the quadratic formula, or I could just use the equation solver on my calculator, couldn't I? I might be tempted to use the equation solver on my calculator for this one. So I've got the 64 million at the end. All right, so we just dive in there, put that in the equation solver in your calculator, or try it by the quadratic formula. So I'm just going to do that away for a moment. I'm going to go to Wolfram Alpha, and I'm aware that you can't see this bit that I'm just doing at the moment, but once I've done it in Wolfram Alpha, it gives me 2 answers. It gives me a minus 1071.8, and it gives me a 14,928. Well, it's obviously the 14,928 that I want. It's got to be positive. So hopefully you've seen that on your own calculators. 14,928. It has to be a positive value. Why is it positive? Because that distance is positive. Negative would take me out the other side. We're not out this side here. Yeah, we're measuring this distance from there to the moon, and that's a positive value. So that is my focal distance. I've worked out it's that number of kilometers. Okay. And there we go. All right, the distance from the moon to the vertex, and that is the closest distance that the satellite gets. Notice to start with, it's at 16,000 to the point we know, and it comes around the curve, and it ends up being as close as that. That's question 3. That is tricky. Certainly doesn't deserve to be that early in the exercise, because there's a lot of thinking about that, getting your trigonometry involved, and then not getting too worried when you can't get just the value of x straight away for the satellite's coordinates. But the fact that it's still got the a in there, we can get that expression, means we can get an equation just with a's in it. Difficult question. Really difficult question, I think. On to question 8. Now, question 8, I think, is difficult for 2 reasons, and probably doesn't warrant being this early in the exercise. The first one is you don't have a diagram. And on most of these questions in this exercise, you're given a diagram. Okay? Mostly you will see a diagram to help you visualize what's going on. Most of the time in the internal, you'd see a diagram as well to help you visualize what's going on. And the first time I tried to draw this, I drew the diagram incorrectly. Okay? We need to be thinking about how the diagram should look, and there are a number of different ways to think about this diagram. And because it's a 3-dimensional situation, we can only really do a plain view of it. You've got to think about which way around do you want to be doing. Do you want to be looking from above the ground downwards, or do you want to be looking across the ground? What are you wanting to do to get this to work? And also another thing why this question is difficult is because it doesn't tell you what kind of curve you're going to get. You've just got to determine a curve at the end of this. All right, it doesn't tell us we're working with an ellipse, a hyperbola, a circle, parabola. We don't know. It's a locus question. All right, so one of the first things we looked at in this particular internal, this particular topic, was to think about how we can determine a rule, turn a rule that we're told in words into something that we can express in a Cartesian form with x's and y's in it. So that's where we've got to go on this. So there's a fair bit of work on this one. So what I'm going to do to start off with, I'm going to start with having to think about my coordinate system and where I'm going to put stuff. So let's start with that out here. Now, A and B are 6 kilometers apart. So I think I'm going to put them here. I'm going to put one of them at -3. And I'm going to put one of them at 3. Okay. And I'm told that this mortar is located 2 kilometers closer to A than B. Now, if this mortar was on the x-axis, that must mean, if it's 2 kilometers closer to A than to B, because I've got 6 to think about here, the split would have to be 4 and 2, wouldn't it? It would have to be there where x is 1. All right? So I'm saying this is A, and this is B, which I should do. Describe carefully where I'm. So when it says this in the internal, if you're asked to do this sort of thing, choose a suitable coordinate system, you really need to explain it in words as well. All right, I'm not doing that right here. A bit tricky for me to draw stuff out on my PowerPoint, but you would do that. So you would say, put A and B along the x-axis such that A has got coordinate x coordinate 3 and B has got x coordinate -3. Start with that. Okay, then you can start. You've got your description, you can do your diagram. But that's really what my diagram's showing. Now, this mortar, though, is located 2 kilometers closer to A than B. It doesn't say it's located on the axis. So it could be somewhere on a curve. Okay? And I can kind of see that curve's going to have to be symmetric. Okay? I can kind of see it's going to have to look the same above the x-axis as it is going to look below the x-axis, because as I start moving a little bit away, being 2 more or 2 less, I can see that there's that symmetry in there. It's got to behave that way. So this is where my mortar could potentially have landed. And I'm going to put this detector aircraft flying at a constant height so that somewhere along the path it will pass directly over the mortar. Well, I can only be sure it's going to do that if it follows this path. Somewhere on that path is where the mortar lies. So if I send my aircraft along that path, it will directly fly over the mortar at some point. It will be able to determine its position. All right, so we know that. Right, so I've got to determine now the equation of this curve. Now I've got a diagram that's going to work for me. I've set up my coordinate system. I've got to determine the equation of this curve. So I'm going to think about a point that is on this curve, and its distance to B, and its distance to A. I know the distance to A is 2 kilometers shorter than its distance to B. I know that distance is 2 kilometers longer. Okay, so as with locus questions, I'm going to start by just saying, well, assume the coordinates of my point A are x and y. All right, x and y are my coordinates. Can I then use the condition that the distance from P to A is 2 kilometers shorter than P to B? That's what we're going to look at. So we'll start off with by thinking about what these things are going to be. All right, so let's start with P to A first of all. Now, when we're working out distances between points, we're really using Pythagoras, if you remember. If I drop down a little vertical there, we're looking at the difference in the y coordinates and the difference in the x coordinates between the points, and they're the sides of my right-angled triangle, the sides that are perpendicular. My hypotenuse will be given by this bit squared plus this bit squared, all square rooted. So just remember, it's all about doing the change in the x value, difference between the x values, the difference in the x coordinates, plus the difference in the y coordinates, both of which need to be squared, and then you square root. Okay, so that needs to be squared, and then we square root. That will give us what PA is. So PA, let's just look at simplifying that. PA is going to be difference in the x coordinates. So one has got x coordinate 3 and the other one has got x coordinate x. Yeah, A is 3, at P it's x. So I can just do x minus 3, the difference between them squared. Okay, the difference of the y coordinates is easy because we go from y to 0 by the time we've got to A. So that's just going to be a y squared. Okay, so we can say that. By a similar argument, we can just write down PB. Okay, what's happening now? Well, the difference between our x coordinates is now x plus 3. Yeah, you should see that gap. It's going to be x plus 3. It has to go all the way back to minus 3 and then up to x. X subtract minus 3, difference in them gives you x plus 3. And we've still got the y squared. Square rooted. So what do I know? Well, I'm told that PB is PA plus 2. Twice as 2 kilometers more rather than. So I can write this down. Now, I'm going to get, it can get a bit messy from this point. So what I'm going to do really, starting out with, I don't like writing down all the square root bit and so on. It just looks a bit untidy. I might do that to start with, but then I might start to just go for some shorter notation, which we've used before. So I know that PA, let's write down, I know that PB has to go here. So that's my x plus 3 squared plus y squared square rooted. That is my left-hand side. Okay, PA was the similar looking expression, but with a minus between the x and the 3. So we end up with that, plus y squared, square rooted, plus the 2. Now, this doesn't help me at all at this stage to see what kind of curve I'm dealing with. All right, if I go back to my curve right up here, if I'm looking at it, what is happening? Is this a hyperbola? Or is it part of a hyperbola with another bit out here, which we're not including? Is it a parabola, where this is the vertex? Don't know. Is it part of an ellipse and I've just not joined it all the way around, so it's come like that? Okay. Now, you might be thinking there's one of those you can rule out straight away. All right, if the ellipse came all the way around here, we're going to have a bit of a problem because, are we going to say that distance is 2 more to there? Well, maybe so. Is it an ellipse? Is it a hyperbola? Is it a parabola? Okay, maybe we've still got all of those to think about. But this isn't really helping me at the moment. However, what can help me is by squaring both sides. Because as soon as I square both sides, I've got rid of the square root on the left-hand side. The square root on the left-hand side is gone. And I'm just left with x plus 3 all squared plus y squared. Now I'm going to take the next bit on the right-hand side a little carefully, because this is where we can go wrong if we're not careful. This is where it gets a bit messy. Now, if we think about what we're doing on this right-hand side, we've got two things added together that we are going to need to square now, because that's what we've done on the other side. We're going to square both sides then, haven't we? So we've got two things added together that need to be squared. So let's just have a think about how that generally goes. If I've got two things added together and I need to square them, how does that go? Well, it gives me an a squared, and it gives me a b squared, and in the middle it gives me a 2ab. Okay, that's what happens if I was just to multiply out that bracket by itself. If you can't remember that, just give yourselves a little bit of, maybe pause the video and just have a look. Multiply out a plus b all squared. It does give you this. Okay, simplified down. So what I've really got here is a is all that square root, and b is the 2. Okay, so I know I'm going to get the square of the square root, and I know I'm going to get 2 squared. All right, this is going to be the square of the square root. That is going to be the 2 squared. So that's quite easy, because I can square the square root again, just like we did on the other side. Minus 3 squared plus y squared. And I can square the 2. The b squared is going to give me a plus 4. But then I've got this 2ab bit that I haven't dealt with yet, this bit here. What's that going to be? Well, a is the whole square root thing, and b is 2 itself. So 2 times the square root times 2. I've got 4 lots of the square root. And at this stage, I'm just going to write square root ... because I don't want to be writing that out every time. I know what that means. It's the square root from the line above, but I'm just making it a bit quicker and easier for me to write down on here. So I've gone from, let's have a look at what's happened on as we move from the line here to the line just below. We've gone from an expression that's got an equation rather that's got 2 square roots to one that's just got 1. So we've made it simpler, but we've not got rid of all the square roots yet. You might be a little bit ahead of me here, might be thinking, well, we need to deal with this square root now. Squaring somehow will help us with that, and yes, it will. But let's tidy up first. Let's make the thing that we're going to be working with to square as easy as possible. So I'm going to multiply out my brackets there. Yeah, x squared plus 6x plus 9 plus y squared. I'm going to multiply out my brackets on the other side. Now, this one, just the only difference between the bracket on the other side when we multiplied it out is we get a minus 6x because of the minus 3. Everything else comes the same. And we've still got the y squared. And we've still got the 4 lots of the square root, which we've not dealt with yet, but we're bearing in mind we're going to need to do something with that. And we've still got the plus 4 at the end. Now I'm going to change colour pens at this stage because I'm going to look at how I can simplify what I've just written down. Well, first thing to notice is there's an x squared on both sides. So let's just take x squared away from both sides. Cancel those out. As minus 6x and plus 6x, we can't really do anything there, but there is a 9 on both sides. So let's get rid of them. Take it away. And there is a y squared added onto both sides. So let's get rid of those as well. Take them away. So we've done some cancelling just to make our lives a little bit easier. Now let's have a look. If I can isolate the square root so it's on its own, then I know I can do something similar to what I did in the first step. If I square a square root and that square root's on its own, the square root disappears. If that was the only square root, I've got no more square roots left. So that's going to help me. So let's get everything apart from the square root across onto this left-hand side. We've got a minus 6x here. How do we get that across? We add 6x to both sides. 12x. Okay, what else do I need to get across? I need to get across this plus 4. Well, I'm going to have to subtract 4 from both sides to get that to go. And that is now equal to 4 lots of the square root. That's looking an awful lot tidier. To tidy a little bit more at this stage, and so I don't make a mistake on the next line, I'm just going to divide through by a common factor of 4. 4 divides into all the terms. The 2 terms on the left-hand side and the term on the right-hand side. So I've simplified down to that, getting my numbers as small as possible. And now if I square, I will get rid of my square root. 3x minus 1 all squared must be just the thing that was underneath the square root. What was I using these 3 dots to mean? I was using it to mean this thing here, what a was, isn't it? Okay, that whole thing in there was a. A was the square root of all of that. So I'm now left with x minus 3 squared plus y squared. Still can't really see what curve this is. At this stage, still can't tell whether it's an ellipse, a hyperbola, or a parabola. Probably suspecting it's not a parabola, maybe, but I don't know. All right, we might have to see. Let's have a look. Let's multiply on out and see if we can get anywhere with that. So we've got 9x squared minus 6x plus 1 from squaring out on the left-hand side, and multiplying out on the right-hand side, x squared minus 6x plus 9 plus the y squared. Right. Now, we're not immediately seeing here that there's anything that we can cancel. I'm going to take all the numeric terms across onto the right-hand side and all the algebraic terms across onto the left-hand side. So this x squared is going to come across onto this side. It will leave me with 8x squared, won't it? Because I've got to subtract that. Also, I should spot at this stage too, I've got a bit more cancelling happening, haven't I? I've got a minus 6x here. I've got a minus 6x here. So if we add 6x to both sides, they will go. Okay, so we got that out. And now, what else are we left with? That plus 1 is going to go across to the other side. The y squared, though, is going to come across to this side. So I take y squared from both sides. We end up with minus y squared there. And I want the 1 to go across with the 9. So I subtract 1 from both sides. I end up with that. Are you seeing what this curve is yet? Maybe if I divide through by 8, you might see a little better. So I'm just going to bring this up here. If I divide through by 8, we have x squared minus y squared over 8 is 1. You're probably seeing at this point that that is the standard form, or in the standard form of the equation of a hyperbola. And that is indeed what we're looking at. We're looking at the equation of a hyperbola. We've got a little bit careful here. If we're going to answer this absolutely carefully, and if we were thinking about excellence here, we might just want to be absolutely sure we're defining this carefully enough. Yes, that equation is true. P does satisfy that equation. But if I was to look at this hyperbola, the full equation would also give me a branch out here, wouldn't it? Yeah, I get the symmetry. I don't get the blue bit, though. So what can I add into my equation just to show that actually I don't mean the blue bit? I just mean the bit that was marked in red originally. Well, all I'm going to say is just take the ones where x is positive. Just take the branch of the hyperbola where the x values are positive, because that gives me this bit. These have all got positive x values. On the blue side, they've all got negative x values. Okay, and I'm done. All right, pretty tough question, though. Right, question 10. I actually think the questions get easier from this point. 3 and 8 are horrible. Really are horrible. Really top-end questions, high-level excellence thinking around those. Let's have a look at question 10 then. So we've got the roof of a convention centre. It's modelled by the top half of an ellipse. I can see that, the yellow bit. The roof rests on a plinth. That's the brown bit. Cuboid-shaped platform that's 4 metres high. Okay, diagram's looking good here. I've got a diagram. Feeling happy. The convention centre is 60 metres wide. All right, you can see that marked on. And the highest point is 19 metres above the ground. Express the equation of an ellipse using a coordinate system that has an orange O in the centre of the floor at ground level. Okay, so let's just tick on with that. Let's have a look at how we can get this on here. So this would be the centre of my ellipse. So the centre of my ellipse, I'm going to know if that's the origin and that distance there is 4 on the end, that I know that the centre of my ellipse is going to be x coordinate 0, y coordinate 4. Okay, I have that. I know that this length of minor axis, the semi-minor axis length there, must be 15. Because the whole height of this thing is 19, and I know that the brown platform is just the 4. So that's 15. And I know that the whole width across here is 30. So if the major axis is, 60. If the major axis is 60 long, then that length there is 30. The semi-major axis is 30. Well, I think now I can say what my equation of my ellipse is. Because I know that the x position isn't offset, the center isn't offset from x equals 0, so that's okay. So I can put x squared over 30 squared plus the y position is offset by 4 though, so I'm going to do y minus 4 squared. That's where my center has gone. And that would be over 15 squared, the length of the semi-minor axis. And that all equals 1. So what am I really saying? Okay, let's just write it this way. X squared over 900 plus y minus 4 squared over 225 is 1. That is the equation of my ellipse. Okay, not too bad doing that. The diagram was drawn for us, put on the information that we know, look at what the semi-major, semi-minor axis is, look at where the center of the ellipse is, and we're okay. Actually, if we wanted to be completely correct about this as well, we'd want to say that in this case, we are only looking at ones where our y value is greater than or equal to 4. Right, otherwise, we'd get the bottom half of the ellipse as well. We just want the top half of the ellipse. All right, so the special machine runs sideways along the 60-meter length of rails on the platform balcony. All right, this is outside this platform. And the machine is used to clean the windows between the roof and the platform. This machine can only reach to a maximum height of 12 meters. So for what length of rails can the machine not be used to clean the windows under the roof? So this machine runs along, and it goes along cleaning the windows. All of this is glass, say. But it can only go 12 high. But this thing is 15 high, isn't it? The thing is 15 high. So we know it's going to reach a point where it can't get the whole of the roof. And there is the symmetry in here. All right, so this bit that I'm marking up here, it would not be able to reach if this distance is 12. All right, that distance there is 12. It can't reach. So let's take a point here, the limit of what it can reach. So my point will have an x coordinate. Be really careful at this point because the y coordinate of that point, look at where we're starting from, where our origin is. Our y coordinate is 16, isn't it? Okay, the 12 and then the 4 for the platform. All right, now we should be able to stick in, work out what x is. Well, x will take me to there, and if I double that, I've got the length. It can't be used to clean all the way up to the top 4. All right, so let's have a look. Part B. Use the equation of our ellipse. X, we don't know, so we've got x squared over the 900 plus y minus 4 squared over 225. Y minus 4, the y coordinate is 16, isn't it? So y minus 4 will be 12. Okay, that is where our 12 comes in. And we've got to square that. We've got 144 then. Over 225 is 1. And we're just going to rearrange this now to say what x is. So let's just go from there. I can say that x squared over 900 must be equal to 1 minus 144 over 225. Now 1 is 225 over 225. If I subtract 144 over 225 from that, 225 minus 144 gives me 81. I'm quite liking this because look at all the square numbers I've got here. So if I just square root, I'm going to get an x over 30 equals a 9 over 15. Let's just tidy that up a little bit to make it even easier for me to move on to the next step. So why don't I cancel that down to a 2 and that down to a 1. So x over 2 is 9 over 1. I think I should be okay then to say that x is 18. So the distance that we're looking for in the question is twice that. Why is it twice that? Because, let's come back to our diagram, the distance is twice that, 36. Why is it twice that? Because this distance here is x, that's x. We've also got x on the other side, because we have got the symmetry, remember. So the whole distance that it can't reach all the way to the top of the roof is 36, the 18 and the 18. Thinking about another way if you wanted to, actually, when I square rooted, don't forget you would bring in a plus or minus, generally. So you would get a plus or minus 18, and you can see it from that way. The total distance then is 36. All right, much easier than question 3 or question 8, I think. Diagram, and we can work from there. Question 14, all right. Bend of a motorway is modelled by one branch of a hyperbola, like we saw in question 8. The line of symmetry, the full hyperbola is a long, high wall placed there for soundproofing and to minimise glare from headlights for nearby residents. So you sometimes get this on motorways. They build a wall so that they're not going to get traffic glare, people who live nearby. In this model, the origin O is the midpoint of the wall, and it's also the closest point on the wall to the motorway. That distance there is the shortest distance. The distance from O to the motorway is 20 meters. So I know that that there is 20. Okay, by the time I've got to there, that distance is 20. The length of the wall is 400 meters. So because of the way the wall is structured, I know that at W1 I will be at 200, and at W2 I would say minus 200, the way that this is drawn. So it's 400 long. The horizontal distance from the motorway to each end of the wall is 50 meters. So I know that this distance here is 50. Yeah. Or if I like, I know the coordinates of M1 are 50 and 200. Getting a point on the curve is probably going to help us, isn't it? All right. So we've just used the information in the question so far to get what our picture looks like, build up some coordinates, sketch on that sketch a little bit more, put some values on it so we can use it, like we did in the last question. It does tell us there's a door, D, in the wall to provide safety access in the case of accidents on the motorway. The door is 80 meters from one end of the wall. So, okay, it's 80 meters we can see from W1. So that must mean its Y coordinate is 120, the 80 meters down from the 200. Yeah, so it says D to W1 is 80. It's telling us that. What's the horizontal distance to the nearest meter from the door to the motorway? So we're after this distance here. So let me choose, again, I'm going to say here's a point P. What do I know about P? I know its Y coordinate, but I don't know its X coordinate. And its X coordinate is actually what I want to find out, isn't it? Because that in there is the distance. The distance horizontally from the door to the motorway. All right, what can we say about our curve? We know it is, we know it is a hyperbola. Okay, we're told that. And so thinking about where the center of the hyperbola is, it's quite a nice one. It's x squared over a squared. Well, I know a, because it tells me the focal length is 20. So I could say x squared over 400 minus the y squared over b squared. I don't know what b is at the moment. I don't think I can read that off anyhow easily. Equals 1. But I know this point, 50, 200. Or I could use for M2 if I wanted minus 50. 50 and minus 200 would give me the same things. So let's use my point, 50 and 200. What's that tell me here? So 50 is the x-coordinate. If I square that, I'm going to get 2,500 over 400 minus y squared over b squared. Well, that's 200 squared. So I'm going to end up with 4 followed by 4 zeros because I had 2 zeros before I squared it. Over b squared is 1. Now I'm just going to do a little bit of cancelling before I try and tidy that up and work with it and solve it. Divide top and bottom here by 100, so I get 25 over 4. Okay, so I come back to my red pen. Now I'm going to take the 40,000 over b squared onto the right hand side, and the 1's going to come onto the left. So I'm going to get 25 over 4 minus the 1. Well, 1 is 4 over 4, just so we can see what we're going to do next, equals 40,000 over b squared. This is going to let me get to what b is, isn't it? Or actually b squared will be enough, because since I've got b squared, I've got the equation of the hyperbola. So what have I got? I've got 19 over 4, haven't I, there? No, I haven't, because I can't add up, take away. Whoops, I meant to get the rubber. There's my eraser, there he is. Usually 25 minus 4 is 21. So let's just make sure we fit in with convention. 25 minus 4 is 21. 21 over 4 is 40,000 over b squared. All right, let's flip everything upside down. So the b squared goes on the top. 4 over 21 equals b squared over 40,000. So now we know what b squared is, don't we? So b squared has got to be 160,000 over 21. So I now have my equation of my hyperbola. My hyperbola is going to have, I'm over there, am I? My hyperbola is going to have equation x squared over 40,000 minus 21 y squared over 160,000 is 1. Now, if you're not sure where this has come from, because it would be over b squared, wouldn't it? On the bottom, you would think over b squared. But if I'm dividing by b squared, if I'm dividing by all of this, I am really multiplying by its reciprocal. All right, divide by a fraction, you are multiplying by its reciprocal. So rather than divide by the 160,000 over 21, I've just said multiply by 21 over 160,000. So I've got the 21 multiplying and 160,000 on the bottom. All right, we now need to know what, coming back to this, it was all about the door, wasn't it? And the distance horizontally of that door to the motorway. This x-coordinate here, where we know that the y-coordinate is 120, so we can put 120 into that and work out the x-coordinate. So we'll jump back in to doing that. So we know we've got x squared over 400 is going to be subtract 21 by 120 squared over 160,000 is 1. Well, it's just a matter of rearranging that and square rooting to get what the x value is. So let's just do that. So if I bring all of this stuff with 120 squared across onto the right hand side and then multiply up by 400 and then square root. Okay, so I'm going to do all that in one go. You can do it step by step if you want. If you want to pause the video and have a look at that. But it's, down to you to have a go at that if you want to do that. Pause the video and have a look, see if you get to the same thing that I do. All I'm doing is bringing this across to the same side as a 1, so it'll become plus, multiplying up by 400, and then square rooting. That'll give me x. So what's it going to tell me I need to do? I need to do the square root of 400. If I'd have thought about it, I could take the 400 outside the square root, couldn't I? But not to worry. Now the square root of 400 is 20, multiplied by the 1 plus 21 by 120 squared over 160,000. All right, so it'd be a question at that point of reaching for your calculator and keying that in. So let me just do that now. Not something I know that off the top of my head. I wouldn't expect that you do too. But let's have a look, see what we can get from that. So I need to type all that in. So 20, so the square root of 1 plus 221 times 120 squared divided by 160,000. Well, and it's a nice whole number. Who would have thought it? X comes out to be 34. All right, if we had played with it a little bit, we might have got an exact square there, we might have spotted it, but it's telling us the distance then is 34 meters. Okay, that distance from the door to the motorway is 34 meters. So that's how far people would have to scramble in the eventuality of an emergency. Okay, 34 seems a reasonable answer as well. If you think, have I done something wrong, always check back to the situation. We know it's going to be more than 20 because it's 20 to that shortest point. I mean, it's going to be less than 50 because it's 50 there. All right, so that seems a reasonable answer, 34 meters. Okay, right, on to the next question. 15. Rugby balls vary in shape and dimensions depending on the manufacturer. Suppose the cross-section of a rugby ball can be modelled by this ellipse. The end-to-end length is 28 centimetres and the width of the widest point is 20 centimetres. The ball is placed upright in a kicking tee. Horizontal line drawn through the top of the tee passes through the bottom focus, interestingly, of the ellipse. Calculate the distance A to B, which is the width of the tee at the top to the nearest millimetre. Okay, so we're dealing in centimetres, be to one decimal place, wouldn't it? Let's just set up our nice coordinate system. I want my centre of my origin, the centre of my ellipse to be the origin. So I'm going to draw my axes there and going down through the centre and through the focus. Okay, and I've got the orientation this way around. Notice I've got orientation so that the major axis is along the y-axis rather than the x-axis, so we'll just need to bear that in mind a little bit later on. And there's my origin. Okay, what do I know? Well, I know that it's 20 centimetres across, so I know that the semi-minor axis there is 10, and the semi-major axis must be 14 because it's 28 from end to end. Well, that means I know what the equation is going to be. It tells me that the equation of my ellipse is x squared over 100, 10 squared, plus y squared over 14 squared, which is 196, is 1. I've got my ellipse. That is my rugby ball. Now, I want to work out this distance across, this dotted green distance here. Now, point B is an interesting point for me because it is on the ellipse. And that distance across there is the x-coordinate of the point B. Do I know the y-coordinate of the point B? Well, actually, I know the y-coordinate of the point B, I'm just going to call it y for the moment, is the same as the y-coordinate of the focus. Yeah, that focus there has the same y-coordinate as B. It's on the same level vertically. So can we say where the focus is? Well, I know A here is 10. I know B is 14. Or I know A squared is 100 and B squared is 196. And I know that the usual relationship is B squared is A squared minus C squared for an ellipse. Now this is where I've got to just bring in the fact that the orientation is the other way around than usual here, because we've got our major axis along the y-axis. So I just need to swap the A and the B round to make it make sense here. Yeah, because where we've got A, we've got B, and so on. Just don't want to get this bit wrong. All right, because the major axis is along the y-axis. So that's telling me that 100 is 196 minus c squared. So c squared is 96. Now, if you'd have done that the wrong way around, b squared is a squared minus c squared, you'd have got into a bit of a mess there. You'd end up with c squared being negative. Can't be negative. It would tell you've done something wrong. It's just that you set the equations up the wrong way around. Okay, set the equation up the wrong way around. And you could probably rectify that quite easily, but just be on the lookout for, if you get any squares are negative, we can't deal with them. Nothing that we've done has said we can do anything with negative squares at this point. Okay. So c squared is 196, is 96 rather. So c is the square root. Now 96 is 16 lots of 6. So c is 4 root 6. Now my position for f shows me it's got a negative y value. Okay, now c is that focal length. So it means that the y coordinate of f must be minus 4 root 6, and it means that is the same for b. So b, I'm now able to say, is the point x minus 4 root 6. Okay, well, let's sub that into my equation that I've got. Let's bring down my ellipses equation. That should let me work out what x is. All right, b is a point on the ellipse, remember, so I can use this. So I'm able to say that x squared over 100 plus y squared. Well, y squared I know is 96. 4 root 6 all squared. Where did that come from? It came from the square root of 96, didn't it? Over 196 is 1. So x squared over 100, and take the other bits across to the same side as the 1. 1 is 196 over 196. And we subtract 96 over 196. Rather nicely, that gives me 100 over 196. Or if I like, x squared is 100 squared. Now 196 there, remember, was 14 squared. So that's going to tell me that x is 100 over 14. Plus or minus, the minus 1 would have given me the x coordinate of a. That's actually 50 over 7, isn't it, if I want to deal with that. And the distance that I'm talking about, the distance from A to B, which is what we wanted to work out, let's go up here then, is twice that x coordinate. All right, the distance from minus 50 over 7 to 50 over 7. So twice the x coordinate be 100 over 7. We wanted this to the nearest millimetre. It says this is all in centimetres at the minute, remember? So we just need to work out what that is. It's going to give us a decimal, and we're going to round it to 1 decimal place because we want it to the nearest millimetre. So we should get that is 14.3 centimetres. And that's what we're asked to work out. Seems a reasonable answer again, because remember the whole distance across the maximum distance across my rugby ball was 14.3 centimetres. Was 20 centimetres. So that being 14.3, that's reasonable. Always check it makes sense reasonably.